Today's lesson, we're going to be looking at the application of vectors. All right. Um, our objective is that students will be able to apply operations on vectors to solve problems, and we're really looking at real life scenario, specifically revolving around archways, like we looked at in the activator. We looked at, you know, a picture of a bridge that had, that kind of arch design. And we're going to talk about the physics of these stone arches. We're going to take a look at this little interactive applet, and we're going to use vectors to represent forces, and we're going to kind of go through and talk about some scenarios as to why arches stand, or why an arch might actually fall. All right, and we'll be looking at this throughout the lesson. So we're going to jump right in. There's a construction of a stone arch, and it's illustrated in an applet from PBS and Nova. And so science and physics and math has helped people to construct buildings over many, many years. All right, and there's real math being applied as these buildings are being constructed, and we see this go way back in time. All right, and there's this thought: we have an arch, right? And I'm going to be able to click on this, and we'll go to an interactive applet. You can access the link to the interactive applet in the additional resources section of the lesson. But we're going to click on this, and we're going to actually take a look, and we're going to see that if we have this arch and it's standing, if the arch increases height, all right, what do you think might happen to the arch? Just by, adding to the base, it's standing just fine like this, but what would happen if we stood it up on, a really tall base like so, and it's much higher? Well, what do you think might happen? Think about that, and we're going to actually do a little bit of an exploration here in just one moment. All right, so I have this applet opened up, and I want to know, how high can it go? What would happen if I perhaps took away a block? Well, you notice it falls immediately, right? What this does is this allows me to kind of explore what would happen if a block were removed, what would happen if we added a block, etc. So I can set this, all right? And notice it says the pursuit of height was all the rage for architects. They wanted to build the highest, or the highest, tallest arches, all right, in the big churches and cathedrals. So we can build a basic arch structure and see how high we can make it go without causing a collapse. So if I say increase a block, that adds a block to my height. Now what happens now? The arch type is rounded. I can make it pointed, so it's like this. Either way, it's not really that important. But we're going to keep it rounded for right now. And we're just going to add blocks. And as we add blocks, the arch gets unstable and collapses. Why might it have collapsed as we increase the height? We added, once I got up to 3 blocks, down it goes. All right? And now what might have happened? Now, I could add something called a buttress. And if we look, a buttress essentially puts more support out to the side. Now watch what happens as I increase the number of blocks. I'm 3 high. I'm 4 high. Adding that buttress caused some additional support up until, I made it to 5 with buttresses. All right? All right, so I know if I have a buttress, I can go all the way up 5. Now I can do this thing called a flying buttress, which kind of adds this other piece out to the side. I can create what's called a pinnacle. All right, if I add that additional piece on top, can I get higher than 5? Notice I get to 5 and it stays. Last time it fell here, so adding just that pinnacle, this extra piece on top here, added some additional support, which prevented this from falling, but we can see it's getting pretty unstable. Well, they came up with this idea of this thing called a flying buttress, and you add that to the side. Now what happens as I continue to add height? Notice I can go much higher. It eventually, at 8 blocks, if I go down to 7, will it stay? It'll stay at 7. All right, so now if they pointed it, maybe you could get a little higher. Nope, it's still going to fall at 8. But anyway, so we're able to really do this exploration and see how high we can get. But what are the forces that are really acting on this arch? What is it that's happening in terms of what we have been studying in terms of vectors? All right, and that's really what we want to explore. Why is it that adding supports off to the side, right? Now what would happen maybe if I took off that pinnacle? Notice, it almost fell, but it didn't. What would happen if I remove the buttress and just had that extra piece? Notice it we needed those supports, but why? What is the math that is happening here that is affecting that arch? That's the question. So the first thing that we want to think about is we need to think about the different forces at play. If I have two stones that are just on top of each other, that can be seen here on the right, all right, we have one stone that has a force coming down. We call it compression, and we have another stone that's providing resistance. Because the stones are not moving, right, we know that the forces, they sum to zero. All right, so whatever force is pushing down, we have an equal force pushing back up. All right, and that's what we have there is that compression and resistance. All right, as we add blocks to this, we have additional forces. And the interesting thing is, as we start adding, pieces out to the side to form an arch, right? Well, they're pulling straight down, but when they're pulling straight down, there has to be, from each block, those same components pushing at each other. All right, so how does that actually come into play? What does that look like? We're going to take a look at what that looks like in just a little bit, but first we want to talk a little bit more about the forces at play and what really results in a stable versus an unstable arch. So for example, we have this thing that we call a thrust line. It's kind of the sum of all the forces. If they're all right down the middle, it's stable. It's not going to fall over. But as we have this thrust from the roof, as we add additional pieces that kind of go off toward the center, that thrust line gets pushed out to the edge. And the closer it gets to out here, the more likely it is for this arch to become unstable. All right, if we can find a way to keep that force into the middle of that column, then the arch will be more stable. All right, so what they found is that if the arch, caused that force to come outside the block, it would cause it to fall over. All right, so what could they do? What could they do to prevent that arch from collapsing? Well, what they did is they started to add buttresses, all right? And that's kind of what we showed. If we were to add this buttress here on the left and on the right, notice where that force ends up. That force now still is contained within that base of the arch at the ground, all right? So that's the whole purpose of the buttress. It's because this force ended up outside of the arch. So essentially it's saying, hey, let's make that base wider so that force is contained. And if that force is contained, it will remain stable. Now, one of the things that they really worked on, that those buttresses evolved such that they could make things even more, even higher and higher up and more impressive. They added this flying buttress where they said, hey, if we could get that out farther, if I know that overall force is going to end up way out here because I have a super high arch, well, I need to have something to support it. So they created these flying buttresses where you would have that additional support right where the force was, so that force was being contained. And so we also had a vertical force here that was contained as well. And so it kind of broke that down. And so long as all of those forces were contained into the base of the arch, the physics of it proved that the arch would remain standing. All right. They created these pointed arches once again to contain that force, etc. It just was another style of those archways. We saw in the example when we added that pinnacle, when we added that additional, stone on top of a buttress, it created just an additional downward force, which kind of helped keep this force more contained. Because we've learned about with vectors, we can add those vectors together, and as we add them together, it kind of changes the final resultant vector. And so that pinnacle is just another force being added together. We can think of these forces in terms of vectors. All right. And so we sat there and we built the arch, and we were able to get things, pretty high. We could get it all the way up to 7 blocks. We've kind of shown that. All right. Now we can explore another example, another little applet that we can adjust the height. But there's one other thing that we can do with this is we can show the forces at play. And we're going to take a look at that. And we can add buttresses. We can do the same thing, but we will also be able to change the weight of the stones, and we're going to explore what will happen as we do that. So here is that 9-stone arch. Let's pull that up. All right, so here we have it. We have this 9-stone arch, and notice I have these different force vectors. As when I click on the force vectors, we can see a couple things. All right, we should be able to note that the blue arrows represent the forces at play with each individual stone in the arch. As we add those forces together, the resultant force is going to be the red arrow drawn. Notice if that red arrow is outside of the base, it becomes unstable. I could add a buttress, and now notice that red arrow turned green because it's now stable because that arrow hits within the base of the archway. As I increase the height, notice what happens. This is what's happening. Notice the resultant vector from the arch is not changing. The only thing that's changing is the height. But that red arrow comes outside of that base, right? If we were to imagine that arrow extending all the way to the ground, it's outside, the resultant force comes outside of the base, which would cause that to collapse. All right, so really the only thing that's determining whether or not the arch stands or falls is its height. All right, and the other interesting thing here is what happens if I increase the weight? What happens if I decrease the weight down? Notice the vector, the direction of the vector does not change, just the magnitude. As the weight increases, the magnitude increases, but notice the direction does not. So even if I put the weight as high as it'll go, so long as that height is low enough, it makes no difference in whether or not the arch is stable. The weight has no impact. All right, I could have the highest weight possible. So long as the height's low enough, we're fine. Once that height vector gets outside of that base at the point where it hits the ground, we're no good. It could be super light. It could be made out of like styrofoam. If that resultant vector is outside of that base, the arch is going to fall. All right, so the weight of the stones bears zero impact on the stability of the arch, which is interesting. And all of this really comes down to is the resultant vector, the sum of all the vectors of the individual components, which is represented by this red arrow. All right, where does it end up? At what point does it impact the ground? And is that within the base of the arch? Is there something there to support it? And if there's not, the arch falls. So how are those forces determined? How were those, when I looked at, the different forces at play in that arch, well, where did those arrows, those vectors come from? Well, if we think about a stone in the arch, all right, it would have a couple stones next to it, like this. All right, now what we know is that within the archway, gravity pulls down. Right? Gravity is pulling down. So we actually have a couple forces at play here. All right? Because we know that the arch needs to be stable in the same place, I need the resultant vectors, the forces on this particular stone that are acting on this stone. I need all of the forces acting on this stone to sum to zero. So what we have is we have a force coming in this direction from the stone to the left, and I have a force going in the opposite direction from the stone on the right. And if I take and I sum all three of those vectors, I just head to tail, head to tail, head to tail, notice we create a loop. They all come back to the same point, meaning the resultant force is zero, meaning the stone stays in the same place. But because we have this force going off in this direction holding it, right? We have these two green forces kind of being pointed in the two different directions. All right? If I have one in one direction, well, I'm going to have one in the opposite direction, because if there's a force pushing to the right on the stone in the middle, then there's going to be a force to the left on the stone to the left. All right, and it's this force going out in that direction. It's the sum of those forces in the outward directions that are going to be determining whether or not this arch stands. So we would take the vectors, that are formed from gravity pulling down and say, well, what are the forces that would have to essentially stabilize that vector, kind of cancel it out, and then know that the opposite force is going to be put in the directions of the other blocks all the way down the arch. And then once we sum all of those forces to the left on the left-hand side, to the right on the right-hand side, we can determine whether or not an arch would actually stand. So this is, a real practical application of vectors that people knew about hundreds and hundreds of years ago, even thousands of years ago, as they built bridges in the Roman times, which is pretty amazing that they were aware of all those different forces. So, we looked at these examples in the applet, and we could see, how and why those particular arches would either stand or fall. All right. So in the lesson, we explored some more practical application of vectors. We looked at, real world scenarios of this math in play. All right. And it's, whether or not you can go out and build a stone arch that's going to be stable, that really doesn't matter. But what's important is that you understand why we learn about vectors, why we study them, because these vectors represent these different forces that are real. And we start learning how we can solve, real world problems that use them. All right, engineers designing bridges, designing different things, they have to know this kind of math because they have to design things such that they won't fall. They have to design things that are going to be safe, that are going to work. And you wouldn't invest in building something if it was just going to fall down the second it was built, right? So this math is extremely important, and it's applicable to many, many things.